Welcome to the next part. Now we are discussing about diffraction of light, phenomena of bending of light waves around the corners of small obstacles or apertures, and spreading of light into the region of geometrical shadow. We call it as the diffraction of light. So just like we are able to hear the sound, even if the source of sound is not in direct line of sight of the observer or the listener, even then the sound is able to reach to the ears of the listener after bending from nearby obstacles or objects. Similarly, the bending of the light wave also take place around the sharp edges of the obstacle or apertures. We call this bending as the diffraction of light. But for diffraction of light to be observed, we had to make one condition satisfied, that is that the size of the obstacle or the aperture should be of the order of the wavelength of the light. If this condition is satisfied, only in that case diffraction of light can be observed.
How can we hear sound when we cannot see the sound player? This is because the sound waves bend around the corners to reach our ears. This phenomenon of bending of waves around an obstacle in their path is known as diffraction. All types of waves exhibit this phenomenon. Observe the diffraction of water waves at a narrow slit placed on its path. When the size of the slit is large, the diffraction of water waves is quite negligible. On the other hand, when the size of the slit is very small, we observe the diffraction of water waves very clearly. The diffraction of waves depends on its wavelengths. If the size of the obstacle or the slit is of the order of the wavelength of incident waves, then diffraction occurs. This condition is also applicable to light waves. The wavelength of visible light is in the range of 400 to 800 nanometer. Since the wavelength of visible light is much smaller than the dimensions of most of the obstacles it encounters, we usually do not observe any diffraction. If a screen is placed behind an opaque object, light from the point source travels in a straight line and forms a shadow on the screen. But if we look at the shadow closely, we observe that no sharp boundary exists between the shadowed and the illuminated regions. The illuminated region above the shadow of the object contains alternate bright and dark fringes because of diffraction of light. And the pattern is called diffraction pattern. Let us now study diffraction of light at a narrow slit. Place a monochromatic light source on one side and a screen on the other side of a narrow slit. When the slit is illuminated by monochromatic light, a diffraction pattern is formed on the screen. The diffraction pattern consists of a central bright band, which may be much broader than the width of the slit, with alternate dark and bright bands on both sides. The intensity of the fringes decreases very rapidly. Let us now analyze the
Fresnel and Fraunhofer diffraction. Diffraction phenomenon can be classified under two groups: Fresnel diffraction and Fraunhofer diffraction. In the Fresnel diffraction, the source and the screen are at finite distances from the obstacle, producing diffraction. In such a case, the wavefront undergoing diffraction is either spherical or cylindrical. In the Fraunhofer diffraction, the source and the screen are at finite distances from the obstacle, producing diffraction. Hence, in this case, the wavefront undergoing diffraction is plane. The diffracted waves, which are parallel to one another, are brought to focus with the help of a convex lens. Fraunhofer pattern is easier to observe practically by a spectrometer. Thank you for watching.
Fraunhofer's diffraction at a single slit. When a monochromatic light wave is allowed to fall on a tiny opening with size in few micrometers, the light undergoes diffraction. Now, if we place a screen in front of the opening, alternate dark and bright pattern is formed on the screen. Now let us discuss about the diffraction pattern formed by a monochromatic light source. Consider a plane wavefront XY of wavelength lambda incident on a narrow slit AB of width small a. According to Huygens principle, every point on the wavefront at the slit will become source of secondary wavelets. Waves of same amplitude are emitted from these points in all directions. With the help of a convex lens L, all these waves are focused onto a screen placed at a distance d from the slit. A diffraction pattern is obtained on the screen, and the pattern consists of alternate bright and dark bands of decreasing intensity on either side of the central maximum. Now, let's calculate what causes these bands. Now consider a point O on the screen which lies on the perpendicular bisector of the slit. The wavelets that fall on the lens L1 parallel to CO converge on point O, since the waves from these points travel equal distances to reach point O. The phase difference between them will be zero. The waves superpose with each other and produce maximum intensity at O. This point O becomes the location of central bright fringe. Now consider an arbitrary point P on the screen. All the secondary waves from the slit AB make an angle theta with CO and reach the point P. The intensity at point P depends on the path difference between the waves. Now let us draw a perpendicular AN from the point A to this ray diffracted from B. Now the distance Bn gives the path difference between the secondary waves from A and B reaching point P. From triangle ANB, Bn by AB is equal to sine theta and Bn is equal to AB sine theta. Since AB is the slit width which is equal to A and Bn is the path difference, therefore the path difference is equal to A sine theta. Now, case 1. If the path difference between the waves is equal to lambda. To analyze this condition, let us divide the whole wavefront AB into two equal halves, AC and CB. Since the path difference between the secondary waves from A and B is lambda, the path difference between the secondary waves from A and C reaching P will be lambda by 2. Due to path difference of lambda by 2, these two waves will interfere destructively at point P. Overall, point P will be of minimum intensity and it is called first secondary minimum, and it is formed on either side of the central maximum. The angle of diffraction theta, for which the first secondary minimum is produced, is given by the relation A sin theta is equal to lambda, or sin theta is equal to lambda divided by A. Since theta is very small, sin theta is approximately taken as theta. Therefore, theta is equal to lambda by A. If the path difference between secondary waves from A and B is equal to 2 lambda, in this case, the wavefront AB can be divided into 4 equal parts. Now, every point in a part will have a point in its adjacent part, for which the path difference is 2 lambda by 4 or lambda by 2. Hence, all these waves will interfere destructively. In general, the angle of diffraction theta n for nth secondary minimum is given by A sine theta n is equal to n lambda, where n is equal to 1, 2, 3, 4, and so on. Now let us find the positions of secondary maxima. If the path difference between the secondary waves A and B is equal to 3 lambda by 2, in this case, the wavefront AB can be divided into 3 equal parts. The path difference between the corresponding points of the first two parts will be equal to lambda by 2. Therefore, they will interfere destructively. However, the wavelets from the third unused part will interfere constructively at point P to produce a weak first secondary maxima. Similarly, second secondary maxima will be formed on the screen where